Hello friends, in last lecture we discussed the types of broadening mechanism. In these types of broadening mechanisms we discussed the line broadening, natural broadening and collision broadening or Doppler broadening mechanism. So, today we are now start to the new article critical population inversion. In last unit we see the population inversion process. In this population inversion process we can see the populations can be generated from energy levels due to the ground state to excited states and according to that of various types of emission processes. So, in this population inversion process, how to critical inversion can be takes place, we let us we discuss about that. So, first we have for define the quantity nth as in the form of nth nth is equal to n2 minus n1 th. This is the threshold condition denoted th denoted by the threshold condition. So, n1 n2 n1 is defined as the population inversion process. So, nth is called critical population inversion. So, it is it represented by minimum population inversion density and required to that of start the lasing action. So, in this critical population inversion condition we get the nth is equal to 8 pi v square time period of t spontaneous y th upon v square g of v, where it is will be denoted by spontaneous emissions of the in the form of the gamma conditions. So, it will be defined as the population density in the form of g of v, where is g of v is the Gaussian unit functions defined in this way. This can be separated between the distance between two levels of that frequency can be occurred. So, that will be the equation first. So, nth is equal to 8 pi v square time t spontaneous of y gamma th del v by v square. So, delta v can be denoted by the in the form of the frequency is the frequency between the two points separations of that the in that case of we get the frequency occurs between two waves separated by delta v. So, in that case g of v forms, we replace g of v by 1 by del v in the above equations. So, that can be denoted by the lasing threshold conditions will be achieved at that central frequency v 0. That in that case v 0 can be defined as the central frequency. So, that the threshold condition th will be defined by the nth is equal to 8 pi v 0 square time period t spontaneous del v by v square as in bracket alpha s minus 1 by 2l in length of r1 r2 between two spaces. So, it will be denoted by the equation third. So, in that case in the mirror losses and the scattering losses are all small of and laser medium cannot be pumped. So, R1 R2 be the distance between two mirrors can be denoted. So, light pulses starting with original field strength E0, and at that time t can be given by. So, we can in this case the original light can be started from that source of light, the stimulated, and light spread in the form of waves. So, in that case the light pulses will be generated in that original case of that field strength is 0. So, T is equal to 2L by V, where L will be denoted by the length of that two mirror distances. So, and V is a frequency denoted. The electric field after one round trip will be given by, in that case the electric field when light pulse is generated, automatically the electric field will be generated. So, in that case E of t is equal to E0 exponential of 2 alpha L R1 R2, that can be denoted by equation 4. In that case the electric field decays with time, and it can be represented by in the time form E of t multiply by E0 exponential of t by Tc. So, it will be Tc can be defined as the cavity of that decay constant, and that value of that electric field will be defined as small t is equal to capital T, will be represented in the form of E of t is equal to E0 exponential of capital T upon Tc. So, in that case we above represent the t is equal to small t is equal to capital T represented, and that can be in the cavity decay constant will be represented as in the form of equation C. So, from equation 4 and 6 we get exponential of capital T upon Tc is equal to e raised to exponential of 2 alpha L R1 R2. So, in that case exponential of in the form of in bracket 2 alpha L ln of R1 R2. So, that equation can be represented by capital T upon Tc is equal to 2 alpha L minus length of R1 R2. So, in that case T is equal to, so capital T is equal to 2L by V. So, in case of capital T is equal to, we can represent 2L by V. So, replace the T in the form of 2L by V. So, we get the equation Tc is equal to 1 by V alpha minus 1 by 2L, and in the length of R1 R2 minus 1. So, this will be represented the equation 7. So, the fractional loss IC per unit that trips will be defined as IC is equal to E0 minus E in bracket capital T upon E0. So, when we get the losses are small, though that will be represented in the form of E of t is equal to E0 1 minus 2L in bracket alpha minus ln length of R1 R2. So, the IC is equal to 2L in bracket V of alpha minus 1 by 2L of length of R1 R2, that can be represent the equation 8. So, we can find out the Tc is equal to IC related, it can be related is defined as Tc is equal to 2L by VLC. So, that will be represented by equation 9. From equation 7 and first equation, we can write the next equation in the form of NTH, threshold frequency. So, it will be represented as NTH is equal to 8 pi V0 square for time period of t spontaneous delta V upon V cube time period T C. So, it will be represented at the equation 10. So, from equation 9 and 10, we get the next the laser conditions of that equation. We get NTH is equal to 4 pi V0 square time period T spontaneous delta V upon V2 in bracket LC upon L. In that case, we represent the frequency and time period of in the form of spontaneous emission, and that delta V will be represented the waves distance between separation between waves, two waves it will be represented. So, that we get from equation 7, we get the laser condition becomes more difficult to be satisfied at the laser frequency mode.